Okay, I'm going to give a few examples of old test problems related to material that we're supposed to know for test 2. So this first example is about a centroid of a triangle. So the centroid of a triangle can be defined to be the average of the vertices. So I take the sum of the vertices, say, of triangle UVW and divide by 3. That will be the centroid. It's the same thing as the center of gravity for the triangle, and we have talked about that a little bit, but this problem, we're not going to use what we mentioned earlier. So if I have a triangle ABC, I want to take the midpoints of the sides. Like usual, MA will be the midpoint of the side opposite A, so it will be the midpoint of BC. MB will be the midpoint of the side opposite B, which will be AC. And MC will be the midpoint of the side opposite C, which will be AB. And we want to show in this problem that the centroid, the center of gravity for the triangle connecting these midpoints, M sub A, M sub B, M sub C, is the same thing as the centroid of triangle ABC. This is just a matter of computing the average of the coordinates, so the average of the vertices. So for this triangle, we want to add MA, MB, and MC together and see what we get. So then we want to divide by 3, but let's work with just adding these together first. So M sub A was the midpoint of BC, so it's B plus C over 2. M sub B was the midpoint of AC, so it's A plus C over 2. M sub C was the midpoint of AB, so it's A plus B over 2. And you can see we have 1/2 A here, another 1/2 A, so that's 1A. We have a half B and another half B, so that's 1B. And we have a half C and another half C, so we have a C. So that's just A plus B plus C. So we have the sum of the midpoints is the same as the sum of A, B, and C. So I just want to divide by 3 on both sides, and we can see then that the centroid for this triangle MAMBMC is equal to the centroid of the triangle ABC just by dividing by 3. So the only real work after this is just to put some English down. So since we have this, by dividing by 3, we get that these are equal. And by definition, that means the centroid of triangle MAMBMC is equal to the centroid of triangle ABC. So that finishes the argument for this problem. Let's do this question. Here I have an arbitrary point A and an arbitrary point B, and really only one arbitrary angle alpha. And for A, I'm trying to prove that if I take, well, let's say a rotation first by about A by alpha, followed by translation by B, that I can put the translation by B on the other side, do that first, as long as I change the point that we're rotating around, still the same angle, but I change the point by adding these two, A plus, make this A plus B. So I don't really have these commute, but I can turn them around as long as I change the point and make this point the sum of the 2 points here. And then we want to use that information to somehow say what this messy product of rotations and translation is. We have a theorem that would tell us it's a translation. We want to also figure out what the C is that we're translating by, and we'll use A to do both of those. Show it's a translation and define C. Let's start with A. We're trying to show this equation here. It would be nice to have B and A, we know what their coordinates are, so I'm just going to give them names. I'm going to call little a, little b the coordinates of capital B here, and x, y the coordinates of capital A. So this left-hand side here, this T sub B will become a T sub little a, little b, and this rotation about A by alpha, the alpha stays there, but the A becomes xy. Because this is the notation we had when we were writing our matrices, so all I want to do now is to write down those matrices. The translation matrix by AB here, you just put A and B here, ones along the diagonals and zeros elsewhere. For the rotation, we use the alphas here for this part, and then we use the x and y and the alpha in this part. But this was the rotation matrix we had that defined what this was. So on a test, you would have those in front of you. You would know the translation matrix and the rotation matrix, so you could write this down. So that tells us what's on the left-hand side. On the right-hand side, I want to do the same thing, write the matrices down. Notice A plus B in this case will be the sum of these two. So we'll have little x plus little a here and little y plus little b. So we can write then that the right-hand side for the translation matrix is the same, T sub a comma b like we had up here. And the rotation matrix, again, we add the coordinates of a and b. We have x plus a, y plus b here. And you're rotating around that by alpha. So we just write down what these matrices are. This one's going to be the same we had before. It hasn't changed, that translation matrix. But this one has changed because instead of x and y, we want x plus a and y plus b. So now you know how to prove this. It's just a matter of multiplying these out and see if you get the same thing when you multiply these out. So no one's saying it's easy, but you can do it. So I'll give you an example. Let's say we took the second element in the second row and second column. So the element in the second row and second column in the product. So that means you're taking the second row here and dotting it with the second column. We would get 0 plus cosine of alpha plus 0. So this dotted with this is just giving me cosine of alpha. That should be the same thing as if I take the second row here and the second column and take the dot product. We'll get 0 for that, 1 times cosine of alpha, and 0 times this. So we're getting cosine of alpha here, and again, when we took this dot product, we also got cosine of alpha. So that second row and second column element of the product is the same. And you can do that for lots of them. Lots of these are easy, but there are some more complicated ones. So let me do one of the more complicated ones. If I want to know what's in the first row and third column of the product, I'd be taking this first row and dotting it with this third column. So, and this first row and dotting it with this third column, and I should be getting the same thing. This looks messier, but it should equal the same thing as this dotted with this. So let's check that. Let's start at the top here. 1 times this plus 0 times this plus a times 1. So we're just getting 1 times this plus a. So we're just getting this plus a. So that should be what's in the first row and third column of the product. Let's check that we get the same thing here when I take this dotted with this. So I'm getting cosine alpha times a minus sine alpha times b, and then I'm adding to that 1 times this. Okay? That looks worse, but let's check. The cosine of alpha times a, notice when I'm taking 1 times this, I have a minus a times cosine of alpha. So we're taking the dot product, so we're adding the cosine of alpha times a will be added when we take the 1 times this. And those will cancel because you'll have a minus a cosine of alpha and a plus a cosine of alpha. So this product will go away, the a times minus cosine of alpha. Similarly, we have a minus sine alpha and b here. But when I take 1 times this, I have a b times sine alpha. So I have a b times sine alpha and a minus sine alpha times b that will cancel. So the cosine alpha times a, the minus sine alpha times b have canceled now with the a times minus cosine of alpha and the b times sine alpha. And all I'm left with is 1 times 1 sine alpha, 1 times x times 1 minus cosine of alpha. And we have extra a here, but we wanted an extra a because we had this a times 1 that was added to this when we got the product up here. So in both cases, you're just getting this plus a. So for the first row dotted with the third column. So we do get the same first row, third column element in the product of these two. So you just check all the product here, multiplying these two out, and check that you get the same thing when you multiply these two out. Not quick, but it's doable. There are ways of doing this geometrically, but that's one way that's sort of just doing arithmetic. So now we want to use A to say something about this product of translations and rotations. So what I'm going to do is to go ahead and use A. Well, let me remind you what A is first. So it was a way of turning these around. So I want to group these two together and use A and turn these around. So I want to put the translation first and then a rotation, but I have to add the 2 points together. So when you're taking a product like this, you can group them any way you want. You can't commute, but you do have an associative property, so you can do any two multiplications that are together next to each other first. So I'm just going to take these first two at the end, the first two that come in our product of rotations and translations, because we read them from right to left. So I'm going to take the translation on the other side using part A, and I have to add these 2 points together. So I'm going to get 1 minus 2 when I add the 2 points together. So I've kept all these others the same, but I put the translation on the other side, and I've added these 2 points together to get 1 minus 2 for the point of, that's the center of the rotation. But now notice these both have the same point here. So if I group these and do this product first, the product of these two rotations now, that's going to be doing a rotation around the point 1 minus 2 by 3 pi over 5, followed by a rotation by 4 pi over 5. So in other words, you're taking the point 1 minus 2, you're going around at 3 pi over 5, and then you continue to go around another 4 pi over 5. So you're going to be going around 1 minus 2 by 7 pi over 5. So the product of these two rotations, since this is the same point, is just a rotation around 1 minus 2, the same point by 7 pi over 5, the sum of these angles. Okay, because you're just rotating around 1 minus 2 by 3 pi over 5, followed by, keep on rotating another 4 pi over 5, and so you will have rotated by 7 pi over 5. Now I'm going to group these together and do this one first, so this translation rotation, and use A again to put the translation on the other side. So I'm going to take the rotation on this side and translation on the other side, but I have to add the points again. I have to use part A here, so I'm going to get 0 for the x coordinate for the first component and 1 for the other. So I get 0, 1 for the sum of these 2 points. The angle stays the same, and the translation point stays the same, but just goes on the other side. Again, now I have the 2 points being the same here, so I'm rotating around 0, 1 by 7 pi over 5, and then I keep turning another 2 pi over 5 when I look at these product of two rotations. So these I can combine to get a rotation around 0, 1 by 9 pi over 5. So I've gotten these and replaced it with a rotation around 0, 1 by 9 pi over 5. Now I have a translation notation, so I can use part A again, put this on the other side. I have to sum the points. I get 1, 2 when I sum those points. So 1, 2 is the center of rotation. It's still by 9 pi over 5, and the translation goes on the other side. Now again, I have 1.12 where I'm rotating around it by 9 pi over 5 and then by pi over 5. So I get 10 pi over 5. So I'm rotating around 1, 2 by 10 pi over 5, and 10 pi over 5 is 2 pi. So I'm rotating around 1 over 2 by 2 pi, and then I have the translation, I've kept the same, but notice a rotation around a point by 2 pi means you're not doing anything. It's just coming up back where you started, so this isn't really doing anything. In terms of matrices, this would be the identity matrix, where you have ones along the diagonals and zeros every place else. You're not going to get anything here when you multiply it by this, except for this. So this is the same thing as just doing the translations then, because the rotation again isn't doing anything. Now what does this mean? You're translating by 2 minus 1. So you're adding 2 minus 1 to every point. And then after you add 2 minus 1, you're going to add minus 1, 3 to that point, and then you're going to add 1, 1. So really all you're doing to each point is you're adding all three of these to it. So that's the same thing as adding 2 minus 1, 1 for the x component. First component, that'll be 2. And then adding minus 1, 3, 1, which will be 3 to the second component. So in other words, this is just the same thing as a translation by 2, 3. I'm going to add 2 minus 1, and then minus 1, 3, and then 1, 1, which is the same thing as just adding these 3 points together. I'm going to get 2, 3. So the product of these rotations that we started with we end up, it equals this translation, so it is a translation, and the C in the problem is 2, 3. It's a translation by 2, 3. So that finishes this problem. Problem 9, this has a picture with it. We're going to start with a quadrilateral ABCD. And the information given is that the vector AB and the vector AD are perpendicular. So you have a right angle here. And the vector CB and the vector CD are perpendicular. So you have a right angle here. And then we look at AC, we take the midpoint, that's X, and we take the midpoint of BD, which we're calling Y. And the problem asks you to prove that this line XY is perpendicular to the line AC, and you're to use vectors. There is a way to do this without vectors, but let's go ahead and use vectors. And let's first write down the given information. So we had that AB and AD are perpendicular. In terms of notation that we've been using in class, this means that the AB dotted with AD is 0. So I can write it like that. And we have that the vector CB and CD are perpendicular. So that means that the vector CB dotted with the vector CD is 0. And the other information we have is that X is the midpoint of AC and Y is the midpoint of BD. This means that X is the average of A and C, A plus C over 2, and Y is the average of B and D, B plus D over 2. So this summarizes the given information, and we want to somehow use that to show that these two lines are perpendicular, which is another way of saying we want to show that the dot product of two vectors here is 0. So let's go ahead and see how we can do that. I'm going to make some room here. And we still are trying to show that these are perpendicular here. You can see that. What I'm going to do is, since both of these are equal to 0, that means that they have to equal each other. Now, this is a little bit risky thing to do in general in a problem like this because I'm losing some information. I'm only using that these two are equal, and I'm not using that they're equal to 0. And the fact that they're equal to 0 is never going to come up. So I happen to be able to get away with losing that information. And now what I'm going to use is that BD here and BD here cancel. So I have BD and a BD there are going to cancel when I multiply this out. And then I'm just going to finish multiplying this out. I have an A squared for minus A times minus A. I have a minus AD. And I have a minus AB. And here I'll have a minus C times minus C, which is C squared, a minus CD, and a minus C times B. Remember, the B times D cancel from both sides. Okay, now I'm going to bring everything over to the right-hand side. I'm going to take the A squared, bring it over here, and take this over here, and look at what we have. So again, I brought the A squared over, and this one I brought it over. Notice I have a B plus D times minus A here, but it's minus that, so it's plus. So I'm bringing it over, I should have a plus A times B plus D, and I do. When I write like this, you can see it's tempting to factor this as C minus A times C plus A, and then to factor out a C minus A. And that's what I want to do. So I'm going to get C minus A times C plus A, which is C squared minus A squared. And then the C minus A, well, I have minus signs here because the minus B minus D here, but this is minus C minus A times B plus D, minus C minus A times B plus D. So we have this is 0. And now the only thing to do is to divide by 2 on both sides. Notice A plus C over 2 is X. And this is minus, in parentheses, B plus D. When I divide by 2, B plus D over 2 will be Y. So I'm going to have X minus Y when I divide by 2 here, and I can divide by 2 on the other side, I'll still have 0. So I get C minus A, and then divided by 2, I'll have X minus Y is equal to 0 here, and this is a dot product, so C minus A dotted with X minus Y equals 0. So this is the vector AC, and this is the vector from Y to X, and so those are perpendicular, and that's giving us then that this line and this line AC are perpendicular like we wanted. So we've shown that xy is perpendicular to AC, and that finishes this problem. I want to do one more example. And this is problem 5 from test 2, 2011. You don't have to read all of this. The main information is here. And the notation is the same we've used before. We have a triangle ABC. M sub A is the midpoint of BC. M sub B is the midpoint of AC. And M sub C is the midpoint of AB, just like we've had before. And we want to do a rotation around M sub A by pi, followed by a rotation around M sub C by pi, followed by a rotation around M sub B by pi. So the first question is, what's f of c? So c goes around m sub a by pi, that'll go to b. Then around m sub c by pi, that will go to a. And then around m sub b by pi, so that will go to c. So c is going to b, to a, and then back to c. So the answer to this is c. So c gets mapped to c. So how is that useful? Well, we can try to do the same thing with d here. Go around m sub a by pi, and then m sub c, and then m sub b, but it looks a little complicated because it takes us outside this picture. And what you really want to think of it is in terms of our theorem about adding the angles, the sum of the angles of the rotations. So the sum of those angles is 3 pi. And since 3 pi is not a multiple of 2 pi, we're going to get that this is a rotation about some point by 3 pi. Rotating around a point by 3 pi, you're going around a point by 2 pi and then another pi. So that going around 2 pi doesn't do anything. So really, this is a rotation around some point by pi. But when we rotate around a point by pi, there's only one point that stays fixed. That's the center of the rotation. And we just said that c is fixed by f. F of c equals c. It doesn't move. So after we do these rotations, which is the same thing as a rotation around some point by pi, c is not changing. We take c to c and it stays the same. So c must be the fixed point of this rotation. So in other words, these rotations multiply together to give you a rotation around c by pi. Okay, so again, because c doesn't move, that c is the only thing that's not going to move under this rotation. And if I put a different point here, that point's going to be the only thing that doesn't move under this rotation. But c doesn't move. C is going to c. So this point must be c. So that immediately tells us where other points go, sort of like on the quiz. If I wanted to know what happened at this point, you do a rotation around c by pi, it's going to go to b. So that means if I do a rotation around m sub a by pi, followed by a rotation around m sub c by pi, followed by a rotation around m sub b by pi, this point is going to b. It's the same thing as rotating around c by pi. If I use this point, you have to rotate around c by pi, you would end up here after doing those rotations. If I take this point as in the problem, I want to go around c by pi, so I should end up at this point. So that's going to be the answer to the problem here. You end up at f of, you end up at f of d here. So that's f of d in this problem. So this d will rotate around c by pi and end up here. And again, that's the same thing as taking d and going through all these rotations. You should end up here, but everything stays in the picture here if you just use that this f is the same thing as a rotation around c by pi. So that finishes this problem, and that'll finish my lecture.